this is where we left off yesterday, right? We have our regression model, simple linear regression, and we have Jeffreys prior, or A Jeffreys prior. And we know that that is not a probability distribution. So Jeffreys prior is not proper, and that breaks Bayes' theorem. So we cannot be certain that this will be a probability distribution. So we need to check or to find conditions, if they exist, under which this is a probability distribution. And that means we need to find whether this integral is finite or not under the prior, okay? And that's what we are going to do now. So we will try to integrate this out with respect to the three parameters alpha, beta, and lambda. And I'm giving out my strategy here. I will try and integrate alpha first, then beta, then lambda. And for doing that, I will do something similar to what we have done so far when we have these Gaussian data, okay? We have this sum in the exponent. So I will try and express, and we have sums of quadratic terms in alpha and beta. So I will try to express those sums as quadratic terms in each one of the parameters, and that will look like a Gaussian, and I know how to integrate those out. Okay, so that is the strategy. So that can be written as so that is, all the sums go from 1 to n. That's over the data, the sample. So I have n alpha square minus 2 n alpha y bar minus beta x bar plus sum of yi square plus 2 beta xi yi. Okay. So I'll try to. I will call that SYY minus 2 beta SXY plus beta square. Sorry, I will call this, yeah. Am I doing that the way I want it? Yeah. Times n with SYY Okay. Then I can write that down as n times alpha minus y minus beta x bar all square. I'm completing the square there, so I need to subtract that term there, and then the other three terms that I have, plus y minus 2 beta s x y plus beta square s x x. Okay, so I'm just completing that square there, and that closes that. Yeah, okay. So now I will expand that square. So now I will complete squares on beta. I've got those. Okay. Remember that. And so if that is true, oops, then I think I can write that down as n times alpha hat square plus just to make sure that I'm not doing anything. Yeah, square. Yep. Beta square. Yep. How can I write it? So this is lowercase sxy. This is an uppercase sxy. So lowercase uppercase, sorry, okay, hopefully that is okay. Let me just double check that I'm not doing anything funny. Yeah. So now I can complete the square. Okay, so I'm completing this square, so I need to subtract that term square, multiplied by s square, and hopefully now okay, so now everything is in quadratic terms of each one of the variables and actually expressed in the usual sufficient statistics. Okay, so now and so that is the reason why I stated my integration strategy at the beginning, because obviously alpha hat depends on, if I can find it, on beta, yeah, okay. So that's the one that I will integrate first. Otherwise, if I wanted to integrate beta first, I would need to do the other, to express that the other way around. But now it's easy because these are just additive terms in the exponential and they're quadratic. So I can integrate that one as a Gaussian. I just need one of those lambdas outside. I can integrate that one as a Gaussian, need another lambda like that. So that is the integral of lambda. I've taken 2 out. Which converge if both, well, I probably don't have to say that, this looks like a gamma. So this parameter has to be larger than 0. And obviously r square has to be smaller than 1. We know that it's between 0 and 1. In any case, that is the case. Okay. So now you can see formally, hopefully, why you need that many observations. If you want to estimate 3 parameters, alpha, beta, and lambda, and you're not willing to put any prior information into your analysis, you need at least 3 data points for the joint posterior to be a valid distribution, so proper. If r square is 1, that means that x and y are perfectly correlated. That means that if you know x, you know y, so there's no uncertainty. That's what this is telling you about the posterior distribution of lambda. It's degenerate. And not only that, we have, just as a byproduct, we have the marginal posterior of lambda immediately. That's a gamma with those parameters. We could find, and I will show you in a second, I won't do it again, the marginal posterior of beta, which is usually the parameter of interest. We've integrated out alpha, so we have the same expression without the alpha and n minus 1 over 2 with the lambda, and all this expression here. And now we want to integrate out lambda to find the marginal of beta, and that will look like a t distribution, right? And that's what it is. So now probably you can realize, so I will show it in a second, how frequent is, and that's one of the attractive features of Jeffreys priors, that when you use Jeffreys priors, you normally, not all the time, but you normally have posterior distributions that are similar to their frequentist counterparts. So now I think I'm in a position to show you if I could find my clicker, which I can't. I don't know where I left it. Okay, so that's what we did. That's the kind of all the algebra leading to the simplification of the exponential. Some of the definitions of alpha hat, beta hat, and r square, using what we know about the sum of xi square minus xy. And that's the final integral. And we just shown that that is proper if and only if n is larger or equal than 3. So we need at least 3 points to have a proper posterior. And obviously it's not written there, but r has to be, or r square has to be smaller than 1. The marginal posterior, again, that can be an exercise if you want to do that. Just integrate out first alpha and then integrate out lambda. You should be able to show that that looks like student distribution. The mean of that student is beta hat, and beta hat is precisely the maximum likelihood estimator, right? It has n minus 2 degrees of freedom. And the precision, the scale parameter is that number there, okay? So the mean exists if and only if n is larger than or equal than 4. So in principle, you could use the maximum likelihood estimator as a point estimator if you're being a Bayesian and you're using Jeffreys prior. Only if you have more than 4 observations, and you get a variance if you have 5 or more observations. Okay? I don't really know what I did with my... Are there any questions so far? So remember one of the points here is to be very careful every time that you use or see someone using a non-informative flat prior. You need to immediately think about whether the posterior is a proper posterior or not. If it is not, then any inferences that you do are meaningless because you don't have a proper posterior. In this case, again, this is obviously a blackboard example, so it might be easy to find out what is going on. But in our more complex cases, like the examples that we did before, where we actually need MCMC to do the stuff, it's not straightforward to know what would be the conditions to find a proper posterior if you use a flat prior. Okay, so it's dangerous. The advantages, or well, the attractiveness of doing that is that normally your inferences coincide, at least numerically, with frequentist counterparts. So that's the reason why these are called objective. So you're relying only on the data, and the posterior distributions look in some cases similar to the frequentist sampling distributions of the estimators. But I think nowadays people realize that that is probably not something that you want, and it's more and more common to use genuine prior information and taking the time to elicit a prior, because also when you're doing that, you're usually thinking about the problem, so it makes your modeling and your interpretation of the output of your modeling a bit more robust. Okay, so but still it's done in practice, and I think it's good for you to know that is an issue. Okay, so now I will not torture you more with derivations and linear algebra, but I will just go through the slides and try to convince you that, of how this linear regression works in practice from a Bayesian perspective. Okay, so we're going back to our general case. So we have y is a vector with dependent variables of length n. X is the design matrix. So we have p minus 1 covariates and 1 intercept, so p coefficients. So X is a vector of a matrix of size n times p. Each column in X has the covariates for each one of the observations. Beta is the regression coefficient, and we are assuming the same thing, that the errors around that line are Gaussian with the same variance. Okay, so the likelihood looks like that. Again, very similar. We could have done this with that notation, and that's, I think, one of the reasons why I won't repeat it again. So it's just as we wrote down the likelihood here, basically, in this shape. It's convenient to try and write the likelihood in the general case in that shape. So in this shape, you know this is the design matrix. So that's X transpose X, your old friend. Beta hat is the MLE, and S is the sum of the square of the residuals. Okay, it's not too difficult to prove these. You just need to expand the quadratic term and complete the quadratic terms in beta, and that will be complete the quadratic terms in beta, and that will give you that expression. Okay. So if you look now, do I have it here? Yeah. Well, I don't have it there, but if you look at the likelihood once we write down the term in the exponent like that, if we plug that in back there, that will look like normal gamma but now a multivariate normal and a gamma. Okay? What that means is that if we use a conjugate prior, so if we use a normal gamma prior, that will be conjugate. Okay? So we have a normal multivariate there of size, in this case, general K. In the specific case of our regression, that will be P. With some mean M. And then we have this precision matrix. Remember, that's what we're doing, the same thing when we have just one dimension. And then our well-known gamma distribution. It looks like that, right? So if we use this prior, the posterior will be within the same family, but with new parameters, okay? And again, I won't torture you with the details because it's quite a bit of linear algebra there. But you can prove that when you multiply the prior times the likelihood, expand the terms in the exponent, complete the squares, and rewrite everything, you will find that that looks like a normal gamma, now in beta and lambda, with these new parameters. Okay, so that doesn't change, that is the same thing. Beta has the original B, and then that is basically the sum of the residuals, and then a term that takes into account the distance between x bar, or the general x bar, and your mean. The precision matrix there, it's again the design matrix, but now you are adding the precision matrix, so this looks very similar to what we had before. And the posterior mean is a weighted average again of the maximum likelihood estimator and the prior mean, and the weights depend on the precisions. Right now the precision comes from the design matrix and your prior precision. Okay, you have the properties of the normal gamma in your handout, so you don't need to learn these or remember these by heart. You just need to remember to know how to use your handouts and distributions. The marginal distribution for lambda is easy to get. That is a gamma with the same parameters A star, B star. And now the marginal distribution for beta, the joint marginal distribution for beta, is this student distribution with those parameters. And that means that a posteriori at least, the betas are obviously not independent, and the covariance between them depends on that matrix. Okay? But in any case, using standard results of the t distribution, you can find the marginal of each one of the betas will be still a t distribution with the corresponding entry of the mean vector, corresponding entry of the mean, of the precision matrix, and then you will have to decrease the degrees of freedom by as many parameters you have integrated out. Okay, so that will be 2a minus p plus 1. Okay. Again, standard analysis. The problem again with this. I will say something about the problem. Just reassure you that the posterior mean is again a weighted average of the MLE and the prior mean, and those are the weights. If you are doing regression, you know that if you're doing regression from a frequentist point of view and your design matrix is of reduced rank, that means that you have collinearity, then you can do nothing about it. You will need to delete or take out one of the covariates out of the analysis. But if you are willing to put a prior precision, then the posterior precision will not be singular. So if you're Bayesians, you can still do inference even if you have multicollinearity. Or in the other, or saying it from another point of view, if you're a Bayesian, you have to be very careful when you set your priors. You still need to do EDA, because if you have multicollinearity there, that matrix will be huge, and that means that the posterior variance will be distorted. Okay? But in any case, you will have a proper distribution for beta and lambda. Okay. What happens with Jeffreys prior? The same thing will happen. Okay. Obviously, this is a special case of the general case. You will end up with a normal gamma distribution, and you can prove that from there. And now the parameters will not depend on the prior because we don't have any prior parameters. But the posterior mean will be the MLE. The posterior will be proper if and only if you have enough data to estimate all parameters. So that means that you have p plus 1, at least p plus 2 points, just like there. And the posterior distribution for the betas will again be a t distribution centered at b hat and precision matrix related to the design matrix. Okay. I think this is the final example I have, and I do have some code for you if you want to use it. So as I said yesterday, the problem with this prior, if I can go back to that one, yeah, is that, okay? You are linking the precision, the prior precision of beta to the precision of the regression. So you're saying basically that the scale in which you're measuring y is somehow related to the scale of the coefficients. And that is restrictive. That usually doesn't make sense if you think about regression. So in practice, what is more common to do is to have independent prior structure. So you have your Gaussian on beta, your gamma on lambda, but they're independent. Okay? This is no longer, just as in the case that we saw with constant mean, this is no longer an analytical posterior, so we will need to use some Gibbs sampling. You could see the Gibbs sampling scheme here, because you have the full conditional for alpha will be that Gaussian with that mean. For beta will be that Gaussian with that mean. And for lambda will be a gamma with all that parameter. Okay, which is what we have here. Okay. So again, this is just looking at the joint posterior as a function of each parameter at a time. In this case, we're taking beta, the whole vector of beta, as one big parameter, and then therefore we will have a multivariate, a p-variate Gaussian in that parameter, and we'll still have a gamma distribution, full conditionals on there. Okay. So the sampling scheme will be start with some arbitrary point for beta in Rp and some arbitrary positive number for lambda, and then cycle through the full conditionals until you get convergence. Okay. So I have a little example of that. It's a bit more complex than that, but it still works as an illustration. So hopefully you will be able to see that. This is a toy example, so you don't. It's not very difficult to understand and probably not too relevant. This data is described there, so it's just producing petrol, from using 3 different materials and then one rating on the process. So we have basically 4 covariates, and the response variable is the octane content of the petrol. Okay. Just to show you how it is. I don't know why I'm recording. So that's the data. We have 82 observations on the 4 covariates and then our response variable. Before running the code itself, I just wanted to show you a little bit of what is going on in the sampler. That is a sampler. So as you can see, it goes through the full conditionals for beta and for lambda. I have another parameter there just to make sure that things were okay. I won't describe that in detail, but it's irrelevant in any case. The give sampler still cycles through the full conditionals and hopefully we'll be sampling from the true posterior distribution. What I wanted to show you, because that probably will be helpful for the projects, is how to do forecast, okay? We usually want to do regression because we want to forecast. Sometimes we're interested in alpha, beta, and the parameters, but most of the time we want to forecast, okay? So in this case, if we wanted to forecast, we would need to find say y new is the new observation, and we want to use x and y, and that is the integral of f of y new given theta. So theta here will be all the parameters, all the betas and lambda, times the posterior distribution given x and y, and we integrate with respect to theta. Okay, so that will be the actual predictive distribution. We cannot do this analytically because we don't have the posterior distribution. What we have is a sample of the posterior distribution. So we use that sample to produce a sample from the predictive distribution. And it works exactly in the same way that you use a sample to estimate a mean. A mean is that integral. If you have a sample and you want to integrate to estimate the mean, okay. So if you have a sample of this distribution and want to produce a sample of that distribution, you just need to plug in your values from the sample of theta into the distribution of y new and produce a sample from that, okay? That's the idea. So if you, hopefully, can everybody see lines 37 to 44? Yeah, back there? Cool. So as you will see, it's that simple. So this is my function for forecasting a new value for this regression, right? The new data is D, and C is my chain, okay? So these will take any matrix of data, new data D, so that will be new values of X, and will produce a sample of the predictive distribution for Y, okay? And that's why I'm cycling here. So I can predict one new value or any number of new values. Okay. So, so I'm taking. This is the number of forecasting distributions that I will do. M. Big M is the length of the chains that I produce from my MCMC, and I will store my samples from the predictive distribution in Y. And if you can see, the way I produce Y is I just run the regression. So this is the mean, the posterior mean, plus a random number divided by the square root of lambda, okay, which is precisely I'm using precisely that. Okay? So it couldn't be simpler. You just plug in the values of your chain into your function, simulate one value for each MCMC cycle that you have, and then you will have a sample from the predictive distribution. Again, once you have a sample, things are really easy. So this is just running the regression. I'm running it for 4,000 times. I have some prior parameters that I use, but again, what I want to do is to illustrate how to do forecasting. These are just the traces of the chains, just to make sure that they converge at some point, and I can see that they converge almost immediately. So I will just burn in a few of them. The first 1,000 I went thin just because I can. I can do inference. So those are the posterior probability intervals of size 95 for the coefficients of the first, second, third material and the condition. So I can make inference about them. They all seem to be significantly away from zero, but material 3 that has 0 in there. I can, if I want to, compare my results with a frequentist analysis. So that's the linear model run on the same data from a frequentist perspective. And I can see that, again, the third material is not significant. So my inferences from my Bayesian model, or at least my decisions from the frequentist model, are similar. But what I probably cannot do very easily with my frequentist model is to forecast. Okay, so here I am forecasting just one new value with the covariates 70.3, 212, 39, and 199 for the three materials and the condition. Again, this is basically just plugging in the values for beta and lambda that I have for every door of the chain. For that value of x, sorry, this should be x new. Sorry. And simulating a normal variate from each one of them. Okay? That is quite fast to do. It is done. And then I can do whatever I want, in the sense that I can estimate the whole predictive distribution, which is that one. Again, to estimate it, I just need the histogram, just like anything. I can see that it's centered at 92. Almost all its mass is in between 90.5 and 93.5. I can have, it's kind of symmetric. That is expected. So the posterior credibility interval, the equally tailed, will be very similar to the highest posterior density interval. And I can calculate those just by calculating the quantiles of my forecasting sample. I can have a mean, I can have a standard deviation, I can have any characteristic of that distribution that I need. Okay? So hopefully this will help you with your projects or your exercises. And that is it, that's the material. Okay, so I think you now have also, well, for some time, the last couple of exam papers, both in the web page and MOL, so you have an idea of what to expect in the exam. You have the solutions to the exercise booklet. Hopefully you have the solutions to the examples and exercises on the notes. So what you need to decide is whether you want to do some revision either next week or on week 12. But that would mean you coming in and asking questions. Okay, if you do that, I will be happy to help. Otherwise, use Mole or email me or come to office hours. So it's your decision. Who wants to have a revision session, say, next Friday? That's one. Okay, that's two. Okay. Well, majority rules. Thanks very much.